Hi, welcome to the Calculus 3 lecture series. And we are in the unit Vector Calculus. This is our lecture number 10. And so in this video, we're going to talk about a very interesting and important theory. We call this the Stokes theory here. Okay, so far, before we introduce the Stokes theory, so in this unit, we talk about the line integrals, and then we talk about the surface integrals, right? So that we have a different type of the line integrals over the scalar field, over the vector field, and the vector field could be conservative or non-conservative. And then the green theory is kind of a combined line, the line integral concept into like the region bounded by the curves here. Then the interesting things about the Stokes theory is the Stokes series is kind of the put together the line integrals and the surface integrals. They have the relations there. So let's take a look. What is this? So let's go ahead, take a look at what is the Stokes theory, and then what is the meaning of it. And then we're going to do some practice problems about it. Okay, so now let's take a look. What is the Stokes theories here? Okay, so in here I have I have a surfaces here. This is the surface area we talk about is the S here, right? So in here, let's see some highlighted points here. So it said S is a smooth, simple, connected, orientable surface and bounded by a simple closed curve. See here, right? That means this series, see here, this is the curve is bounded by. So it's kind of like the half of surface, right? It's bounded by this curve. And in this R3 here, right? So in this dimension R3 here, F is PI, QJ, RK. And so this PQR, we call this components functions, right? So finally, we suppose like this curve here is, do you see here, like this curve is kind of rotating counterclockwise. So this curve is a positive orientation here. And then we said, hey, if you want to integrate, so here is the key things, right? So here they said, if you integrate in this vector field along this curve, so the left-hand side, this is a line integrals, right? So it tells you, say, hey, here, this will be equivalent to, you take the surface integrations of the curl of this vector fields here. Okay, so this is what we said the Stokes theory is kind of combined of the line integrals over and line integrals and the surface integral concepts here. Okay, so now in here, I have I did some so let's take a look at the next pages here, right? So this is kind of like the progressive, what we learn here. So we said first here, so we start out we said the green series, right? Related a double integral over a plane region to a line integral around its plane boundaries by the curves here. Okay, then the Stokes series, we said related a surface integral over a surface to a line integral along its boundary. So it's kind of like put the green series to the 3 dimensions here. So now what is the meaning of that? We said that in the vector field, the curl, we say, is the tendencies to rotate, right? So we said is the curl of the vector field and the normal vector have the same direction. So we said the curl has the maximal value if the way you rotate have the same direction as the normal vectors, right? So that means that the tendencies to rotate will be vary from point to point on the surface. Then the Stokes series say the collective measurements of the rotation tendencies, right? So over this surface, is it really is just equal to the tendencies of the fluid circulate around the boundary of the curves here. That is the physics meanings about the Stokes series here, right? That's what is the, if you go back, take a look, the the integration. So this is line integral, right? So the tendency is rotating on the boundary curves here will be the overall tendencies of rotations over this surface of the curves here. Okay, so this is kind of like the explanations about what is the curl and what is the Stokes theory, try to relate the the line integral into a surface integral here. Okay, let's take a look at several problems here. Let's try to do see if we'll be able to do that. So let's say the first one's here. Let's say, hey, evaluate the line integral of FDR and the surface integral of curve F. And in here, if my vector field is defined as Y, Z, and the case here in the hemisphere, that means in the half of the above the hemisphere of x squared. So instead of a sphere, just a part of it, right, half of it. So it's x squared plus y squared plus z squared equal to 1, and z is greater than 0. That means it's sitting on top of the xy plane. And the C is the boundary of the S, all right, and oriented counterclockwise. So basically, this is what we said is the hemispheres, right? So it's the half of the sphere sitting above the XY planes here. That's what is this one here, tell you here. Okay, so now we said let's try to do the line integrals and the surface integral. They're supposed to be the same, right? Let's take a look here. So we know the boundaries for the half of the sphere sitting around, okay, sitting around the XY planes here. So we know the boundary. So the boundary curve C is what? It's a circle, right? So it's x squared plus y squared equal to 1 here. Okay, so remember, okay, so the line integral, you can change it to the parametric form. So this one is a pretty easy parametric form. So I would say the x equal to what? xt, okay, and y equal to what? Yt here, right? So what is the xt will be here? Because it's a circle, we know the polar coordinates is always pretty good. So this will be cosine what? Cosine t, because r equal to 1, right? And the y is equal to yt here. So y equal to what? Sine t, right? So what is my t here from 0 to what? 0 to 2 pi here, right? So I parameterize this paths here. So now I can write it, this is the RT, will be equal to what? It's a cosine t and the sine t. Good? And then we, just like we did before, so R prime t, this will be negative sine t, cosine t, right? Okay, so now we need to plug in the parametric representation to my vector, so RT. So this one will be, first I coordinate is y. So what I have here, I have sine t, because y. The second coordinate is z, right? So the second coordinates is z here. So we have the z is equal to what? 0. And the third coordinate is x. X is what? Is cosine t, right? Then based on our integration line integral, so we say it's f dot dr, correct? Okay, so that means now I change everything to a single function t. So this will be the sine t 0 cosine t dot r prime. What is r prime? Negative sine t cosine t, the dt's, right? And what is t? T is from 0 to 2 pi here. So if you simplify a little bit, so let's do the dot product here. So this is 0 to 2 pi. So this is negative sine squared t. And so this is negative sine squared t. So so I'm missing one values here, right? So my here, so here the RT, so Z, sorry here. So the Z here will just be 0, right? Because it's on the XY planes here. So now here, this is equal to 0, much better. So now here, let's see here, this will be, so I need to be careful when I do these things, right? All right, so this is the cosine T, then is 0, then dt is here. Okay, so this is sine square. So 0, 0. So this is good. So it's a negative sine square t. And then you can use like a double angle to change this to a lower power. And then finally, you will get the, so this is the, so the final integration will be 1/2 of t minus 1/4 sine 2t, right? I use the double angle formula to replace it. So this is 0 to the 2 pi. So my answer here is negative pi. All right, so this is by the line integrals here. All right, so now let's take a look at part B here. By surface integral, let's kind of refresh our memory. So for the surface integrations here, then the first things we're going to do is what? We need to kind of change to the, like the UVs, right? So we need to do the RUV. All right, and the RUV, and this is half of the sphere. So I know the spherical coordinates probably will be pretty good. So the now here, x here, we say x equal to the function of the UV, and the y is equal to the function of the UV. And now what is z? Z is equal to the function of the UV. And then here, the sphere is rho r equal to 1, so it's rho equal to 1. Okay, so now I can use the spherical coordinates. So the x equal to what? Rho cosine u cosine v, right? Cosine u cosine v. The reason why we put it here is 1, right? Because the radius is equal to 1. So what is the y? Y is sine u, right? Cosine v. And the z is u and the sine v's, right? Rho and the sine v's here. So this is, we try to use the spherical coordinates ideas, right? Okay, so we said after we do that, the hardest one is try to find the region. So here, this one is pretty easy. So u is from 0 to what? 0 to pi, right? Okay, so the 0 is from 0 to pi, and the v is from 0 to pi. The reason why this is from 0 to pi, because I'm looking for is only half of the sphere, or otherwise it's typical from 0 to 2 pi's, right? Okay, so now that's good. Now let's take a look. So see, that's why the surface integration sometimes is a little bit more tedious. So I know the RUV is equal to the cosine U cosine V, and this is the sine U cosine V, and this is the sine V, so, right? Okay, so now we do the partial like we did before. So first is a partial to U. So this will give you negative sine U cosine V, right? Then this one I do U, so this will become cosine U cosine V. This one do U is will be 0, good. Now I do the partial for V. Let's take a look at partial for V. This one will be the cosine U cosine sine V, right? Cosine U, and here it will be sine V. And then, oh no, here I get a, okay, so here I need to go back to the here. Okay, so it's a cosine. Okay, so let's see here. Okay, do V, so it's a negative cosine U sine V. Okay, I'm right here. All right. Okay, so this one's here, take a look at the V. So this would be negative sine U sine V. That's right. Okay, then the sine V, you take the derivative, will be cosine V. That's right. Okay, so now we do the RU cross RV. So basically, you put this into our, like the things here, we say this is negative sine U cosine V, negative cosine U sine V. Then J is here, this is the cosine U cosine V, negative sine U sine V, and this is K0 cosine V, right? I assume everybody still remember how to do the cross product, right? So now finally I can get this cross product after simplify it. This will be the cosine U cosine square V to the i's components plus, okay, plus sine U cosine square V to the j components, then plus sine V and cosine V to the k components, right? It's a kind of a tedious here. Then also we need to find the curls, right? So the curl, because the Stokes series will tell you will be the surface integration to the curl. Okay, so now let's do the curl of the f. So if you still remember, the curl of the f is also this matrix here. So the first one is you use this operator, del operator, right? So dy rho z, then this is yxz, right? Yxz, that's your vector functions. And then in here, you will get this one's here. You will get this is negative I minus j minus k here. All right, so finally, right, so we can do the surface integration. So it's S, then this is the curl of the F dot of the ds. So basically, we just replace the, the regions. Here is the curl of the F, right? So curl of the F, and then you dot product RU cross RV. Right, then you do the integration of the dA, so region C is here. Okay, so now because UV is here, remember we say this is the one, right? You change it to a UV, the point here is changed to a simple integration, 0 to pi, 0 to pi. So if you plot all these numbers in there, you will get this is a negative cosine U cosine square V minus here, right? The sine U cosine square V, then minus the sine V cosine V, right? All right, so this is a big integration, then you do du dv. So even it looks like a pretty complicated, but now you simplify everything to the u and the v, then you can just use the simple integration we learned in the calculus 2, do a double integration, and amazingly, this will turns out to be negative pi. So from this example, we kind of proved the how to use the Stokes series, right? Okay, let's take a look at the next ones here. So the next ones here, let's say use the Stokes series. So in here, we're going to find the line integral of the f for this path here. Okay, so along this path. Okay, so over the vector fields x, y, y, z, x, z. And z is the counterclockwise triangles and bounded by the plane x plus 2y and plus 4z equal to 8 here. Okay, so in here you have, Here you have a few different ways you can do it, right? So the first one's here, right? So you can do, yes, you just do the line integrals. So, but you have 3 lines, yes, this one, this one, this one. So each one, you need to do a parameterizations. Okay, that's kind of probably will end up to be pretty, it's a pretty tedious job, right? Okay, so now let's take a look, say, hey, maybe I can use the Stokes theory, try to find a surface integration. All right, so for the surface integration, okay, so let's see here. So for the curl F here, right? So the curl F here, so that means I need to do this IJK things again, right? So this is rho X, rho Y, rho Z's here. Then here is X, Y, Y, Z, and X, Z's here, right? So the curl of the F, and if you substitute and we get it so this will be negative y to the I minus z to the j and minus x to the k. All right, so this will be my curl of the f here. Okay, and so for the curl of the f here, right? So now we need to do the surface integrations here. So for the surface integrations here, right? So we want to do that. So the surfaces here, so we know the x here is equal to x UVs, right? So the surface is here. This is my surface, x plus 2y plus 4z equal to 8, right? So I can say x equal to a minus what? 2u minus 4v. So I can say x, y equal to u, and z equal to v. All right. So that's pretty good, right? So, okay, so now I can say here, so u is y, right? So y, I can say the u is here. So u is from 0 to 4. Then v is here, right? So v, let's add x equal to 0 then. So v is equal to what? Is from the 0 to where? So you use the yz's, right? So you use this line, right? So you use this one. So v is equal to the 2 minus u over 2. Like I said, this is the most important ones, right? So it's the boundaries here. Okay, so now let's see here. So RUV, so the RU, okay, so now I can write the RUV. This is A minus 2U minus 4V. Then this is U, this is V, right? Okay, so then the partial U here is negative 2, 1, 0, correct? Yes, and then partial V, okay, so you take the derivative of V, the negative 4, 0, and the what is 1, see here. Okay, now do one more time, and the RU cross RV. So the same one is IJK again. So this is 2, 1, 0, and then negative 4, 0, 1. Okay, so I calculated this one to be the I plus 2J plus 4K. Gee whiz, I finally, that's right, finally we can do that. Okay, so now finally we turns out here, let me separate that one out. So finally the surface integration of the curl F, okay, dot ds here. So it will be my UV regions here, right? Okay, so the curl of the F here, so this will be negative y, so it's a negative u, negative z, so it's a minus 2v, negative x here, right? So the negative X here is what is A minus 2U minus 4V, then dot R cross RU cross RV dot 1, 2, 4. Oh, okay, du dv. Right? Okay. So the let's say the dv du, because the v's have the range of u's is 2 minus u2, and this is 0 over 4. Okay, so let me write this one down here so be clear. So this is 0, 4. This is 0, 2 minus u over 2. All right, so you dot the product and simplify it. It will give you the 7u plus 14v minus 32 dv du. See here, now you change everything to a simple two variables integration, the typical integration. So you just integrate the dv and be careful about the upper bound. Now the final answers here, after you put the, after you integrate here will be negative 160 over 3 here. Okay. Right, so this is how do we do the, the Stokes theory to help to simplify. If you want to do the line integral, perfectly fine. So that means you're going to have 3 lines, right? The first one is C1 is here, C2 here, and C3 is here. So you need to do the parameterization 3 times and then substitute there and integrating 3 times here. All right, so let's take a look at another problems here. So the another problem here is I want to try to find the surface integration of the curls of the F. And my vector fields, this is my vector field. And S is the, is the parabola. So it's in this surface, it's touch the XY planes here, all right? So now let's see what is the curl for the, what is the surface integrations for these problems here, right? So this one's here, probably, because if you want to do the curl, you need to do the parameterization of the surface. So probably will be a lot easier if I do the line integrals here, because these line integrals here, this is my C's, right? So in here, because this is a parabola, so I'm very easy to find this line integral. What is this line integral? So z equal to 0, right? So I have 0 is equal to the 4 minus x squared minus y squared. So I know this line integral is x squared plus y squared equal to what? Equal to 4. Then I know how to parameterize these ones, right? So this is a circle. So the x equal to xt. So what is here is 2 cosine t. Then y is equal to what? Yt is equal to what? 2 sine t here, right? And then here, of course, t, this is a circle. So it's from 0 to 2 pi. So now my rt will be equal to the 2 cosine t, 2 sine t. Then r prime t is equal to what? Negative 2 sine t, 2 cosine t, right? Now it will be pretty easy. You just what? You just put back to the what is your functions here, fr, right? So because they want us to find these ones here. So by the Stoics theory, I know this one going to be equal to what? It's the C f what? dRs, right? Okay, so now let's take a look at the f of dr. So first one here, let's put the f of the RTs there. Okay, so the f of the RT, because this one's here, so I know that in here, the RT, so my Z components is what? Z components is 0, right? Because it's in here, this is 0 equal to Z. So here, I can do the same way. So this is my 0 components here. Okay, so now you put it in here. So you put in the f of RT, you plug x minus y is here. So x minus y, so it's 2 sine minus cosine, right? So it's 2 x minus y. So the first one is 2, like here, this is cosine t minus sine t, right? So this will be your I components, and then plus y minus z. Y, so y is just what? It's just 2 sine t's, right? So it's 2 sine t minus z is 0. So this is my j components. Then k components is x minus z. X is 2 cosine t. Z is equal to 0. So this is my FRTs here. So if you write here, you can take the 2 out, right? So this will be cosine t minus sine t. And this is sine t, cosine t, right? Now the last things here, what I do here, I do a dot product of what r prime t's, right? So it seems it's always the same old, right? It's always the same things here. So it will be this vector dot product, this one's here, right? So if you do the dot product and simplify it, well, we can simplify this is 2 for the 4 sine square t. Okay, so these integrations, it will be simplified to here, right? Okay, so this will be simplified to here. So this will be equal to 0 to the 2 pi and the 4 sine square t dt. You see here is a lot easier than you do the surface like integration, right? If you do surface integration, you have several steps. First, you want to find the curl of that. Then you need to parameterize the surface, and then you increase one more variables, right? Okay, so now this one here, you use a double angle. Also, you can find out, and this will be the 4. This is 1/2 t, right? So that this is 1/2 t, and minus 1/2 sine 2t, okay? Then it's from the 0 to 2 pi. So the answers here is 4 pi. Okay, so as you can see from the, the Stokes theory, so sometimes if you want to find the surface integration, if it's satisfied the Stokes theory, you can just do the line integration. And so for this examples here, the example number 3 will show you the line integration is way easier than to do the surface integration for the curl. Then the problem number 2 here will show you, hey, so for here, the line integration probably is more tedious because you have 3 pieces of the lines in order to do that. So for this one, probably will be easier to do the surface integrations. Okay, that's it. That's it. So what we call it is the Stokes theory, and it's a very handy and useful theory, and it can help you to simplify some of the integrations by seeing where you want to integrate. Sometimes the line integral is easier, sometimes the surface integration is easier. All right, that's it. So it's very exciting to talk about this Stokes series, very nice series here. All right, that's it. And I hope you guys have a good day here. And looking forward to talk about our last topic, the divergence series here. Okay, bye.